Hi there and welcome to this video for Senior Physics on electromagnetism and electricity. In this video we're going to explore the phenomenon of magnetic flux. Now basically magnetic flux was discovered by Wilhelm Weber 1804 to 1891. There's a photo of him on the right hand side. Now basically what magnetic flux works on is the principle that a magnet will generate a series of field lines which are coming out. Now we saw that in the previous video when we looked at magnetic fields. And what a flux does is to try and determine the number of field lines per unit space. So we're looking basically at the density of those magnetic field lines within a specific area. Now this can be calculated using the following formula. Now the formula is psi, which is the magnetic field flux measured in Webers, equals the magnetic field strength B times the area. Now the area is going to be measured in meters per second, and the magnetic field lines will be the number of lines per square meter, so it's Webers per meter squared. So basically we use psi equals B times A to work out our magnetic flux. Now this will be useful to us later on when we look at Faraday's law. Now, as well as knowing that, we also need to know about our magnetic field strength, or B, which is the number of lines per flux per square meter. Now that was determined by Nikola Tesla, 1856 to 1943. He's down in the bottom right hand corner here. Now the magnetic field strength is given the symbol B and is otherwise known as the magnetic flux density, or the number of lines per square meter. So basically what we've got is this was then turned into the units Tesla, and its SI units for this are newtons per meter per amp. So we now basically have our magnetic field strength B, which is measured in Tesla. We also have our magnetic flux, which is basically measured in Webers. Now to reiterate what I've just basically said, here's a diagram which will help us explain what we mean by magnetic flux. Now you can see in here we've got a magnetic field which has been generated, and the lines basically are denoting those magnetic field lines. Now basically we're going to take two areas, area A and area B. So you can see that the areas are the same, but we're moving from a low B area to a high B area. You see in the first diagram on the left hand side here, we've only got two lines in the area A, but when we move to the second section on the right hand side, you can see that we've got 5 lines. So as we can say, within that space we've actually increased by 3 magnetic field lines. The lines have got denser together. There's more lines in the same area, just like we look at when we look at density. If you remember, density is basically calculated by the mass and the volume that it takes up. The greater the mass and the smaller the volume, the result is that all the particles are close together. Exactly the same with magnetic field. And it's this movement from an area of large magnetic field to an area of low magnetic field which actually is very useful to us as physicists to basically determine the idea of generating a change in flux. That change in flux gives us energy, and as a result that can be converted into a force which can be converted into electricity. So as you can see, there is a real good reason why we need to know something about the magnetic flux. So basically, to reiterate, the more lines per specific area, the greater the magnetic flux, and vice versa. So you can go from large number of lines to small number of lines and back again. So let's look at a quick example as to how we can calculate the magnetic flux. So in this example, we've got a uniform magnetic field of field strength 5.5 times 10 to the negative 4 Tesla. If an area within the field is defined as having a length of 0.2 meters and a width of 0.1 meters, calculate the magnetic flux. Well, we know that magnetic flux psi equals B times the area. Now the area is length times width. So basically what we can use is use our formula, psi equals B times A. We know that our area will be 0.2 times 0.1, so our area is going to be 0.2 meters squared. We know that our field strength is 5.5 times 10 to the negative 4 Tesla, so it's 5.5 times 10 to the negative 4 Tesla R field strength times the area 0.02 meters squared. That gives us our magnetic flux of 1.1 times 10 to the negative 5 Webers. Okay, now what I suggest you do is then have a look. I've put together some exemplary videos which literally will run through 2 extra problems for you to have a go at. Then also I've put together a worksheet for you that you can download. The answers are there, so download the worksheet, have a go at the questions, check your answers, and if you have any problems, you by all means you can email me or get in touch with your teacher and they'll basically explain what's going on. These are standard questions. They hope to increase in complexity so that you can go from a C grade up to an A grade question. Well, thank you for joining me. I look forward to you meeting again, and we'll look at another phenomenon in the electromagnetism and electricity unit. Thanks for watching.